Hi, and welcome to today's video on OCR A Level Chemistry. This is the first video in this series, and in this video, we're going to be looking at the first section, Module 2.1, which is Atoms and Reactions. And this is the first video in a series of about 4 or 5 videos. So let's start with atomic structure. So we're starting with 2.1.2, which is atomic structure. Now, I'm not going to be doing 2.1.1 because that's a bit of a history lesson which I don't want to do at this time. So that will be covered in a separate video. But this is the first video which is about atomic structure. So here we have an atom, or the basic structure of an atom. And here we can see it's made up of 3 different types of subatomic particles, as we call them. The first one, let me zoom in. So this is a helium atom. Specifically, this is a helium atom, but you don't need to know that right now. So this is a helium atom, and we can see it's got 3 different types of subatomic particles. These ones, which have a plus, these are called protons. So this is a proton. The other ones in there, and I'm gonna label them with zeros, are neutrons. Now, protons and neutrons, when they're in the middle like this together, they form the nucleus of the atom. So it's a bit like a nucleus of a cell if you do OCR A Level Biology. If you do A Level Biology, it's a little bit like a cell, sort of, where you have the nucleus sort of in the middle, and then everything else around it. So it's pretty much in the shape of a cell, where you have, this is the nucleus. I'm not going to do a biology lesson in a chemistry. And then the cell membrane is kind of like an orbital cell, or an electron cell, this is called. So these are, with minuses, these are electrons. And electrons orbit the nucleus in what's known as an electron orbital. Orbital electron cell. So there is the structure of an atom. Now, protons, neutrons, and electrons, they have different charges, and they have different relative masses. And that's what we'll explain by using this table down here. So protons, neutrons, and electrons have different masses, and they have different charges. So a proton, because I drew positives on there, protons have a +1 positive, have a relative charge of +1. Neutrons have no charge. Electrons, because of the minuses, they have a relative charge of -1. Now, if we go to relative mass, protons and neutrons have the same relative mass of around 1 mass unit. And we write this as 1 mu. So mass units is what the units we use to measure the relative mass of both protons, neutrons, and electrons of all subatomic particles. Electrons have a relative mass of something like 1/2000. I was going to write it as a decimal, but I have no idea what 1/2000 is as a decimal. Well, I can't work out in my head. That is 5 times, which is 5 times 10 to the minus 4. That is roughly 1, 2, 3, 4, which is roughly this many mu. So 1/2000 of a mass unit. So in theory, that means that 2000 electrons weigh the same as 1 proton. And 2000 electrons weigh the same as 1 neutron. Which means if we go back in terms of electrons, if we were measuring the nucleus here, this is a bit off to the side. In terms of electrons, if we were measuring this nucleus, we have 2 protons and 2 neutrons. Remember, 2000 electrons equals 1 proton. So this is 2000 electrons, this is 2000 electrons, and also 1 neutron is equivalent to 2000 electrons in terms of relative mass. So this is another 2000 electrons, this is another 2000 electrons. So in total, the nucleus will weigh the same as about 8000 electrons. It's a little bit of a extra info, or a little bit of an interesting info when you're there. So now we're going to talk about isotopes. So isotopes, one of the many key definitions that you need to know. There are lots of key definitions in chemistry that you need to know. So isotopes are basically the atoms of the same element, but they have a few different features. So isotopes have, number one, different masses. Number two, number of protons. So I'm going to write this as N of P, which is number of protons, equals N of E, where Np is number of protons, Ne is number of electrons. So number of protons is always equal to the number of electrons, but the number of neutrons, different numbers of neutrons in the nucleus. So those are what isotopes are. So we describe all elements, some of which have isotopes, using two numbers. These are the atomic number and the mass number. And to explain this, I am going to, not do that. If we look at the periodic table, we can see how, so periodic table, any element in the periodic table is written in the following format. So you have the element symbol, which I will represent by, so this is how you always write, how it's always found in the periodic table. No, I don't need orange. Let's do dark green here. So this is how every element in the periodic table is written in the periodic table. So this big H that you can see here, this is the element symbol. And I will show you an example of helium, which we have up there. Excuse me. The A, as I mentioned, is the mass number. And I'll explain what these are in a moment. The Z at the bottom here is what's known as the atomic number, or proton number in fact. Now, What do mass number and atomic number mean? Mass number, actually I'm going to write it in shortened form. So mass number A is equal to total number is equal to N of P, number of protons, plus the number of neutrons, which I will denote as N of N. So N of N. So N of P plus N of N, where N of P is the number of protons, N of N, and N, or simply, is the number of neutrons. So that is, and together, these two make up the mass number. The atomic number Z is equal to the number of protons in an atom. And as we discussed earlier, where the number of protons is always equal to the number of electrons, regardless of what isotope it is, the atomic number also tells us how many electrons are in the atom as well. So this is some key information here. So let's go with the example that I have. Actually, here they're using the examples for carbon. But we're not going to do carbon, we're going to do helium, because helium, I think, has only the one isotope. So it will be fine. So if we look at helium, so if we turn to helium, see the root in the periodic table, which is here. So helium you can see has the chemical symbol He. So helium, so let's write that. So like this is this is how helium is written in the periodic table. So helium here, so let's label all of our parts. So here we have the element symbol. For helium, this is for helium. Now, the mass number tells us how many protons and neutrons are in the nucleus. So if we go back up here, you can see that we have 2 protons and 2 neutrons, which must mean that 2 plus 2 is 4. So here we can clearly see that from the mass number we have 2 protons and 2 neutrons in the atom of helium. The atomic number down here, what does that tell us? Well, it tells us the number of protons, which also tells us the number of electrons. So if we go back up here, the number of protons is 2, so that bit's correct. Remember, number of protons always equals to number of electrons, which in this case is also true. So that bit is all fine and correct. So we have 2 protons and 2 electrons. Whoops, I needed this. So we have 2 protons. So this atomic number tells us that we have 2 protons and 2 electrons. And then this here is the chemical symbol. Okay, so now we're going to talk about, so that was about just atoms as they are. We're now going to talk about ions. So ions are a little bit different because they have charged particles. They're essentially charged particles. And it's a result of how many atoms react, of how atoms react. So for example, if you had Na sodium reacting with chlorine, it would react together to produce Na plus and Cl minus. So we're just going to look at one of those. Let's look at Na. So I'm going to draw up a little table. Just to demonstrate this. And that is very wonky. Yeah, that is wonky. But who cares? We're just going to deal with it. So this is Na. So if we look at our periodic table, which I should have kept open, which is not what I'm accustomed to, we can see that Na is 2311. Na is 2311, so Na, this is just the atom, 2311, and this is Na plus, but also 2311. Now let's go through atomic number, mass number, protons, neutrons, and electrons. So here we have the atomic number, which is, I think I labeled it as Z. So here we can have Z on this side. Actually, let's do another nice straight line. Let's complete this table, shall we? I don't know how many. 1, 2, 3, 4, 5, 6. Just be 1, 2, 3, 4, 5. Let's fit in there. 6. And then let's move you down a bit. There we go. Okay, so here we have our atomic number. This is going to be our mass number. This is going to be our number of protons, our number of neutrons, there we go, and number of electrons, and then charge as well. So let's go through Na, the atom. So here we have the atomic number. We can see that the atomic number here is 11. And we can see here our mass number is 23. Same thing here. We have atomic number 11, mass number 23. Remember, the atomic number always, first thing, is number of protons. And in a non-charged atom, or in a neutral atom, in fact, the number of protons always equals the number of electrons. In this case, the atomic number does not change regardless of however many electrons, whether it's charged or not. The number of the atomic number does not change, because that always tells us first thing is the number of protons. So, from that atomic number, we can see that there are 11 protons in the atom of sodium and 11 protons in the ion, the charged ion of sodium. Now we're moving on to number of neutrons. This is where we need to do our small maths, which is 23 minus 11, and that gets us to 12 for both of them. Now, number of electrons. In a neutral atom, remember, in a neutral atom, the number of protons always equals the number of electrons, which means here the number of electrons is also 11. When neutral atoms react with other neutral atoms, such as sodium reacting with chlorine, Na reacting with Cl, Na, in this particular case, Na has lost one electron to form the plus ion. And we can see that because it's a plus ion, that means it has more protons, which are positively charged, than electrons, which are negatively charged. which means that I must have lost an electron, which means that I'm going to write it in a different color. Now we have 10 electrons. You can see here that it's lost an electron. It's gone from Na0 to Na+. That doesn't mean it's gained a proton. The number of protons stays the same. It's the electrons that are involved in the reactions. So, as we will see later, well, not in this video, but in later videos, it's the electrons that get lost in chemical reactions. So here we're going from Na0 to Na+, which means we've lost one electron, which means that the number of electrons has gone down, which means we've gone down from whoopsie doodles, which means we've gone down from 11 to 10. That should be slightly better clear. That might not be clear. If you want any help, go to page 35 of your textbook. There's a good learning tip there that will help you understand this. Now the overall charge here is for the neutral atom because it's neutral and because number of protons equals number of electrons, the overall charge here is 0. Here, there are more protons than electrons, which means that here in this situation, in the iron, we have gone up to plus 1, which 11 minus 10, which is plus 1. Okay, so that's atomic structure. Now we're going to look at, so that was atomic structure. Now, now we're going to finish off by talking about atomic masses. And some other key definitions that you need to be aware of. So we have 3 more key definitions, and these always get asked every time. Whenever I see a paper, this question almost always comes up. Relative isotomic. What is the define relative atomic mass? Define relative atomic mass. Define any mass. That's why these ones are so important. Every past paper I've seen comes up with the question: define relative isotomic mass. Define any of these. That's why these are so important to be able to memorize. You must memorize these definitions. Literally every paper I've seen has this question. Define relative atomic mass. Da, 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 da. Define relative atomic mass. And they're usually like 2 or 3 marks because they're looking for the specifics of each specific part of the definition. So, relative isotopic mass. Even I can't speak my P's and M's properly. Anyway, relative isotopic mass is the mass of an atom of an isotope compared with 1/12 of the mass of an atom of carbon-12. So carbon-12 is the standard for measuring atomic masses. So an atom of the carbon-12 isotope, I'm just reading from the textbook here, is made up of 6 protons, 6 neutrons, and 6 electrons. The mass of an atom of carbon-12 is 12 atomic mass units. 12 U. All atomic masses are measured compared with the mass of a C12 atom. So relative isotopic mass. So mass is the mass, not the mass, the mass of an atom of an isotope compared with, and I'll show you where the marks are because I think it's 3 marks. These are normally come as very easy 3-mark questions. Compared with 1 12 of the mass of an atom of carbon 12. Now, I'll show you where the marks. I'm going to use green, the light green, to denote each mark. So, you get 1 mark here for the mass of an atom of an isotope. Or just, yes, that's 1 mark. The second mark, I'll denote in the darker green. You have to say it's compared with 112. That is a separate mark. 2 marks. The third mark is the mass of an atom of carbon 12. That is where the third mark comes in. So these are easy 3-mark questions to do. Define relative isotopic mass. The mass of an atom of an isotope, 1 mark, compared with 112 of, second mark. The mass of an atom of carbon 12, third mark. 1, 2, 3, full marks. Literally every paper I've seen, I know I keep saying this, but that's just why it's so important, these definitions. Every paper I've seen has this sort of question. Every paper I've seen. Literally every year. I think they ask it like every year, I think even. That's why these definitions are super crucial. Anyway, that's isotopic mass. But I think I've seen isotopic mass much and atomic mass much more than molecular mass and the formula mass. Anyway, relative atomic mass of an atom is the weighted, weighted mean mass of an atom of an element compared with 1/12 of the mass of an atom of carbon 12. Compared with 1/12 of the mass of carbon 12. Again, the definitions, the marks as follows. So it's the weighted mean mass of an atom of an element. There's the first mark. Compared with 1/12. Second mark. Of the mass of carbon 12. Third mark. So basically, the second 2 marks are literally the same. So the second 2 marks are the same things. It's the same for both. It's the first mark that you need to. So essentially, you just need to remember the first mark is different for both, but the second and third marks is the same for both. It's the same for both. So here you can see the mass of an atom of an isotope, 1 mark, compared with 1/12, second mark. The mass of an atom of carbon 12, third mark. Second and third, and then here also, the weighted mean mass of an atom of an element, first mark, compared with 1/12, second mark. Of the, you can see it, the second mark is the same, and the third mark is the same. Only the first mark is different. So you can easily get at least 2 out of 3, if not full marks, if you remember the different sections for the different phrases for the first mark. Now, relative molecular mass is, so I'll give you an example. So if you have, for example, so the MT, relative molecular mass, you add together the relative atomic mass of each atom making up a molecule. So MT So MT is equal to sum of all relative atomic masses of each atom making up a molecule. Making up a molecule. And just to finish off with this video with an example, if you don't know what I mean, let's do which one shall we do? Let's do, I'm gonna briefly have a look. I'm just gonna have a look at say we see which one we can do. Let's do N2, nitrogen. So for example, we look at N2, nitrogen. So if I want to find the MT of nitrogen, N2, you would first do 14, which is the relative atomic mass of nitrogen, and because there's two nitrogens we can see here, you do 14 plus 14, and that's equal to 14 times 2, which is equal to 28. So MT of nitrogen is equal to 28. Okay, so that's the end of. So that's relative molecular mass. There's also relative formula mass, which is mainly used for ionic compounds. So relative molecular mass is normally used for simple molecules such as N2, O2, CO2. Relative formula mass is used for giant structures, as we'll see in module 2.2. So substances like NaCl, that's a giant ionic lattice structure. So you can't do the relative molecular mass for that. You have to use, it's similar, but this relative formula mass is specifically for giant structures. And molecular mass is simply for simple molecules such as nitrogen, or such as N2, or H2, CO2, or O2 even, or CO2, H2O. All of those compounds which exist as simple molecules, they all use this relative molecular mass. Anyway, that's going to be it for this video here. Thank you all very much for watching, and I'll see you. Hope this was useful, and I'll see you in the next video. Goodbye.